Lesson 9.3, exponential growth and exponential decay. We are going to take a moment here and look at the, the stuff that's written up here already worked out for us. In the exponential decay, growth and decay formulas, I want you to underline right now. In the exponential growth and decay formulas, y equals the final amount. It's important that we understand that y is going to mean the final amount, whether it's money, people, grams, whatever it turns out to be. Y is going to represent the final amount. A is going to represent the original amount, which should make sense to us. We've been saying all along, A represents where it starts. That's what original means. Where did it start? And R is going to represent the growth or decay as a decimal. So we're going to have this formula we're going to work with today, and we need to understand the parts of it. So R is the rate. What percent is it growing at? What percent is it decaying at? But then we change it to a decimal, it says. And then T in the formula is going to represent the time. How long? So our first one is exponential growth. That's why we do a little line between those. Let's separate those. We really have two different situations going on here today. We have exponential growth. Would you put a great big fat arrow by that to point that out to yourself, because it's kind of hidden there. Exponential growth. Here's how you will use it. In other words, this is no different than our exponential model. Y equals AB to the x power. We still have an A in it. There's our A. And notice, what did our B change to? 1 plus R. So our B is the 1 plus R part. We still have a B. It's just that now we're going to take the rate, change to a decimal, add it to 1, and then we'll have our B value. And the T is really the what? It's the time, which is taking the place of the x value. Okay, so this is not really something we haven't already kind of worked with. It's just that now it's just breaking it apart a little bit more. So when we have exponential growth, and we have that 1 plus r, that means our b value has to be what? Between 0 and 1? Or greater than 1? What happens when you add a positive decimal to 1? Are you going to get a number between 0 and 1? Or are you going to get a number greater than 1? You better get something greater than 1. 1 plus a positive number doesn't have to get larger, doesn't it? Even if it's a decimal, it still has to get larger. Okay, so here's our situation that they have worked out here for us. And don't be working down there at the bottom. Stay with me, please. The population of a city is increasing at a rate of 4% each year. Okay, it's telling us it's increasing. So our final answer better be larger than what it started at, right? So in 2000, there were 236 people in the city. What do you suppose that 236,000 people, what part of the formula do you think that's going to represent? The A. That's our starting amount right there. That's our A. Write an exponential growth function to model this situation. Oh, well, let's also look at this right here. What do you suppose that 4% is going to be? It's going to be the R after we do what? Put it as a decimal. So let's write that right here. R equals, what's our R value? 0.04. 4% as a decimal is 0.04. Okay, here's the kind of tricky part. When we kind of went through this, it was either yesterday or the day before, I don't remember. It's the population is in the year 2000. They want us to figure out the population in the year 2009. So does that mean we use 2009 as our T value? No. No, what do we find out when we tried to do that before?
How many years are between 2000 and 2009?
So 2000 is kind of like the starting time. It's like time 0. So this 2000 is really saying that's where we're going to start at. So if we want it in 2009, what's our T value going to be? 9. 9 years will have gone by. So notice they have kind of done some of the same stuff. Identify the variables, substitute in, And then they put in, they added the 0.04 to the 1, which made the B value then 1.04. And now the only thing left to do is to substitute in the 9 for the T. And the population will be, it says right here, about 335,902 in the year 2009. Is that a reasonable answer? Does it make sense that the population would be 335,902? We didn't even check out their arithmetic, but does that answer make sense? Why? Don't make this complicated. Why does that make sense? It's just a simple statement. Why does it make sense?
Because.
Where did it start, Caitlin?
Because it's decreasing. I meant increasing.
The population is increasing. Where did it start, Caitlin? It started at 236,000. 9 years later, it's at 365,902. Does that make sense?
Yes.
Yeah, because it did get larger. It increased. If you ended up with a number less than 236,000 with a 4% increase, would that be a problem?
Yes.
Better be, right? Okay, now they do a situation where the population is decreasing. And notice what is different about the formula. What's the only thing that's different when there's a decrease going? You're subtracting R instead of adding it. So in other words, you're going to take away that percentage, change to a decimal, take it away from 1. Okay? And so this situation starts in the same year, but now this time they want to figure out the population in 2012. Has a different starting amount. There's our A value. Our R value is 6% this time, so 6% as a decimal is 0.06. T would equal what? What would T equal in this problem? 12. Okay, without even looking down at the answer, if there are 35,000 people to start with and the population is decreasing at 6% per year, what better happen?
Better get smaller.
Better get smaller. Better end up with a number less than what?
Less than 35,000.
Less than 35,000. So, and notice, it did get less than 35,000. And notice something about the B value. Where is it? What is that B value? Is it greater than 1?
No.
It's between 0 and 1, between 1 and 0. Hey, tell me something, without us being getting real fancy here, tell me something about the graph for this exponential growth one over here. What would it do?
It would rise.
It would rise from left to right, wouldn't it? As time goes on, the population would increase. Oh, by the way, can there be negative x values, do you think?
No.
Negative t values?
No.
Actually, what we could do is we could say, oh, well, if we want to go back a few years from when it started, we could kind of use this model to also predict what was the population before 2000. So in reality, we kind of can. And then over here, what should happen with the graph?
It should fall from left to right.
It should fall from left to right because it is decreasing. Okay, now let's go down and do 1 and 2. Okay, number 1, annual sales at a company are 372,000 and increasing at a rate of 5% per year. After 8 years, you're supposed to, it says write an exponential function to model the situation, then find the value after the given amount of time. Now, notice what they just said, you guys. We're not going to substitute something in for t right away. They want a model that would work no matter what the time factor was. Okay? So, what is this 372,000 going to be in our formula?
Your A.
This is our A value. What about this increasing at a rate of 5%?
That's going to be your R.
R, so R equals what?
0.05.
0.05, and if it is increasing, that means we're going to add that to 1 or subtract it?
Add.
We're going to add, okay? And right now, we don't even care about the 8 years. Don't even pay any attention to that for right now. I just want you to write a model without worrying about the 8 years. I crossed it out for a moment, because I want you to write me a model that does not have that 8 in it. So, y, the final amount, equals what?
372,000
Times
parentheses
1.05.
And what else?
t.
To the t power. We'll clean that up a little bit. We're still not going to use the 8 yet. We're going to clean that up so that we get a b value. So we have y equals
372,000 times t.
to the t power. And if you change that to an x, it's not the end of the world. It's okay if it's an x. Okay? Because this is really our exponential model. Y equals a times b to the x power. Okay, this is the exponential model. So I want you to put an arrow by that, and I want you to write behind it. This is the exponential model for this situation. We just did that part of the directions. And that's where students get points taken off on the quiz, is because when it says write an exponential model for this situation, in other words, it should work for no matter what number of years you want to use it for. Okay? So here's the model. So if I said to you, find the sales after 5 years, you could use this model. What would you do?
Put 5
Put 5 over t. If I said to you, find the sales after 13 years,
13.
you put 13 in for t. But now they want us to do it for after how many years? 8 years. So now we are going to use our model, putting in 8 for t. So y equals 372,000 times our 1.05 to the 8th power. And we're going to round that to money terms. Now I will let you put this all into your calculator at the same time if you're careful about it. Okay? I won't make you show me the steps in between. So what do we have to, how should we put this into our calculator?
Do the 1.05 times 8 first.
Yeah, sometimes
To
I
the
think
8th power.
to the 8th power, not times 8. 1.05 to the 8th power, enter, get that, and then go back and multiply it times the 372,000. That might be the safest way. Doesn't mean it's the only way. Rounded to the nearest cent. To the nearest penny. We should all get the same answer. To the nearest cent, you look at the thousandth place and round it to the hundredth place. Does our answer seem reasonable?
Yes.
Because
Definitely.
increasing. Got bigger, supposed to, yeah, got larger, was
I
supposed
didn't
to.
get that.
You didn't get that? So, what are we supposed to do if probably what you need to do is put a time sign. Are you trying to put it all in at one time and not hit enter in between? Okay, so 1.05 raised to the 8th power, not times 8. Okay, enter.
Yeah, I got one.
Times 372,000. Maybe you didn't put enough zeros in. Okay, now we got it? Okay. So again, really, really important that you have 2 answers for this one. 2 answers. What's the exponential model that we could use for any given amount of time? Because that's the only thing that's ever going to change in this problem. The percent of increase is going to stay the same. The starting amount is going to stay the same. The only thing that should change is how much time, which then will tell us the final amount. Okay, I want you to try the next one in your own then. This is a decreasing one. Be careful. Decreasing. There's a different model to use for that one.
Get the right button.
Okay, so when you head into your model, I want you to verify that you agree with me. And remember, when it's decreasing, what are we always going to count on the B value? Where should the B value be when it's decreasing? What else should be a set of parentheses, and what else should be true about? What should we always count on? Should be as a decimal, or in other words, it should be between 0 and 1. Yeah. So you can think of it like money. It's 90 cents, 98 cents between 0 and a dollar. 98 cents between there somewhere? I hope so. Okay, so when it is decreasing, this, I'm making a point here, this number better be between 0 and 1. If it's not, you did something wrong. When it's increasing, what should that number be? Greater than 1, because it's increasing. Now we'll use our model, and we'll put in 5 for T. And we are talking about people here. So when you do it with people involved, what do you have to do?
Whole number.
Whole number, yeah. We talk about whole amounts of people. And so we have to round, most likely. But we're rounding to the nearest whole person. So what can we say?
I got
1,000.
Yeah, I got 1084.
People. Okay, we'll just round up to the nearest whole person or down to the nearest whole person according to, you know, that's always a kind of a questionable thing. Should you round up or should you round down when you're talking about people?
It's time to
So
actually include.
we're just going to go with the decimal in the tenths place and say, is it large enough to call it another person? So was our tenths place large enough to call it another person?
Yes.
Yes. And we're going to call these are participants, is what they are. So we're going to give them a label. The last one was a money label. This one is 1,085 participants. Okay. So really, really important that we understand when should we have a B value greater than 1, when should we have a B value less than 1? Should our answer final amount be larger than the starting amount? Should it be smaller? Make all those connections. Don't just shove some numbers in and call it good.